So here's the thing about AI that keeps safety researchers up at night. We have this incredibly powerful systems at making decisions about healthcare, education, science, and we generally don't understand how they work. Not in a it's complicated way, in a we literally can't trace logic way. Today I want to walk you through some research from OpenAI that, and I'm emphasizing might, offer a path toward AI systems we actually understand. Okay, let's start with why this matters at all. Currently, neural networks are like imagining trying to understand how a city works by looking at every single electrical connection, water pipe, and data cable, all simultaneously. Everything connects to everything else. Each neuron in these networks connect to thousands of others. And here's the real kicker. We didn't program these connections. The AI learned them through training, which means when GPT-4 decides something, we can't just look inside and see why. In other words, we've built some incredibly powerful thinking machines whose thought processes are completely opaque to us. Now, there are different ways to tackle this. You've got your chain of thought interpretability, basically asking AI to explain itself, but that's like asking someone to explain their intuition. Sometimes accurate, sometimes not. What OpenAI's team is doing here is different. They're going for what's called mechanistic interpretability, actually reverse engineering the computations at the most granular level. So here's really the clever bit here. Instead of trying to untangle existing dense networks after the fact, the researchers asked, what if we train neural networks that were simple from the start? They trained models where, get this, 99.9% of all possible connections are forced to be zero. That's right, out of every 1,000 possible connections, only one actually exists. Think of it like this. Instead of every neuron being a Swiss Army knife, doing 50 different jobs, each neuron becomes more like a specialized tool with a specific purpose. And what they found is sort of remarkable. These sparse models can achieve similar performance to dense models, but when you look inside, you can actually trace the logic. These circuits are about 16 times simpler for any given task. Let me show you something beautiful. This is an actual circuit they extracted for a simple task, predicting whether to close a string with a single or double quote in Python. The model sees an opening quote, either single or double. Step 2 is the two neurons fire. One says, I see a quote. The other says it's a specific type. Step 3, an attention mechanism, basically says ignore everything in between, find that opening quote. Step 4 is copy the type forward and output the matching closing quote. That's it, 12 nodes, 9 connections. You can literally trace the logic with your finger. And here's how we know this is real. Delete these specific connections, the model fails at that task. Delete everything else, keep just these connections, it still works perfectly. Now, let's look at something more complex. Counting bracket depth and nested list. The models need to output either right side bracket or two right side brackets, depending on their nesting depth. And here's where it gets interesting. The circuit they found literally counts. There's a channel that acts as an open bracket detector. An intention head averages this detector across the context, basically counting brackets. Another head threshold, this counts to determine if we were in a nested list. But here's like the really fascinating part. Once you understand this algorithm, you can break it, add comment lines with extra brackets. The model gets confused because it's taking a simple average, making the list too long. The signal gets diluted. Now, before we get too excited, let's talk the trade-offs of this. Making models sparse enough to interpret makes them incredibly inefficient. We're talking hundreds to 1,000 times more compute for the same capability. In other words, these interpretable models are nowhere near GPT-4 scale. But here's the interesting bit. As you scale up the total parameters while keeping sparsity constant, both capability and interpretability improve. There's a frontier here, and bigger sparse models push that frontier forward. The question is, can we scale this approach to frontier models, or find ways to extract sparse circuits from existing dense models? The team's also working on something called bridges, ways to map between sparse interpretable models and existing dense models. Imagine being able to trace specific behaviors in GPT-4 by mapping them to understandable sparse circuits. Personally speaking, I think this is one of those research directions that could go two ways. There's an optimistic scenario where we've developed a library of circuit patterns that appear across scales. We learn to identify these patterns in large models. We actually get mechanistic understanding of complex behaviors. And then you have the pessimistic scenario. The complexity requirements for frontier capabilities fundamentally resist simple description. What works at small scale breaks down when you need to model the full complexity of human language and reasoning. Look, we're still in the early days. These sparse models are tiny compared to what's deployed in production. But for the first time, we're seeing neural networks where you literally can point to specific connections and say, this is why it made that decision. If we can scale this, and that's a big if, we might actually build AI systems whose reasoning we can verify, debug, and trust. In a world where these systems are making increasingly important decisions, a difference between seems to work and we know exactly why it works might be everything.